Hi. My name is Bensu, and I'm a postdoctoral researcher at MIT with the MIT Concrete Sustainability Hub, and I work with Hessam, and today I'm going to talk about our work on a carbon uptake estimation for the US building sector, going from single building elements to the national building stock. So as Jamie's mentioned in his presentation as well, there's a variety of documents that talk about calculating carbon uptake in cement-based products, such as the IVL report. And the Tier 1 approach that Jamie also talked about in this report says that the annual carbon uptake is roughly 23% of national calcination emissions, stemming from the carbonation of existing building stock that is currently in use or reaching their end-of-life stages. And this percentage derives from a variety of different studies. And it's an arithmetic average across a variety of geopolitical contexts, and that's not the only point where it's kind of like comparing apples and oranges, because the percentage is meant to represent a percentage of calcination emissions that are getting recarbonated, captured through recarbonation. But several of these studies calculate the percentage for production emissions, which include calcination and fuel emissions. And the report corrects for this using a factor. It's also comparing apples and oranges in terms of the percentage is meant to represent the existing building stock. But several of these percentages were calculated from a life cycle perspective, looking at 100 or 60 or even 50 years of the life cycle of 1 year's production. So there is some confusion or equating of impact year reporting and product year reporting, which is more similar to what we see in life cycle assessment or environmental product declarations. The objective of our work is to create clear guidelines for carbon uptake estimation so that we can evaluate the potential for carbon uptake, or the carbonation potential, as Craig called it, for neutralizing cement emissions. And for the remainder of this presentation, I will focus on process or calcination emissions. Then we can inform methods for environmental product declarations and greenhouse gas accounting, and engage stakeholders throughout the built environment to leverage the properties of cement-based products to reach their carbon neutrality targets. As I mentioned, the cement emissions could be broken down into process emissions or calcination emissions and fuel emissions, and the process emissions are approximately 55 to 60% of the cement production emissions. So taking those emissions, we've seen global studies report that 43% of these emissions are neutralized through carbon uptake. And that got reinterpreted as 50% in the IPCC report and got updated at 60% in a more recent study as well. And estimating, finding the right percentage for how much is getting neutralized through carbon uptake is particularly important because that also gives us an estimate of the portion of process emissions that remain and further need to be reduced to achieve carbon neutral cement or construction materials. So it's crucial to create a realistic estimate of carbon uptake, because an underestimate of carbon uptake understates the benefits of cement-based products, whereas if we overestimate carbon uptake, then that understates the needs for emissions abatement solutions. To produce this realistic estimate, we employ a bottom-up approach, which makes use of data and modeling to characterize archetypes and the context that they're found in, to assess individual units of these archetypes. On a high level, these archetypes are buildings, pavements, and other infrastructure like pipelines. And more specifically, for instance, for buildings, this includes single-family dwellings versus multifamily dwellings versus commercial industrial buildings at various sizes. So after assessing carbon uptake for these individual units, we can scale it up to meet regional or national scopes. So with the previous studies, researchers employed a top-down approach where the entire national stock is modeled as one huge surface, and at end of life, the crushed concrete is treated as very finely ground and spread out, so there's no really space limitations, and all of this crushed concrete is exposed to be carbonated. With our bottom-up approach, we treat the national stock as a combination of archetypes, which are represented as a combination of archetypical surfaces, as the amount of surface area and the exposure conditions are going to vary for floor slabs versus exterior walls versus a foundation. And at end of life, we treat the crushed concrete as a mix of sizes, and it's stockpiled. So not all of the concrete volume is exposed to be carbonated. Both of these are incorporated into the carbon uptake tool that Jamie was talking about in his presentation. And like the drawings that you guys can find also on that tool kind of represent the geometry of the stockpile that we've assumed. So carbon uptake occurs during various phases of the cement life cycle, and phases with significant amount of carbon uptake include the production of concrete and mortar through the carbonation of cement wastage, the use of concrete and mortar applications such as the carbonation of structural concrete, concrete blocks, plastering and rendering, and the end of life of these materials. And we employ formulas that are also used in the advanced methods that go into reports like the IVL report and IPCC report, the formulas from the EN 16757 standard, where there's a variety of factors that define the relationship between carbon uptake and characteristics like the compressive strength, the material definition, and the exposure conditions. We make use of local market data on cement consumption or production to inform the material definition as well as the volume of cement, because the volume of cement directly scales the amount of carbon uptake that possibly could occur. And the material definition includes information, for instance, about the binder content, both the amount of binder and the percentage of cement that's found within the binder. The different colors on the states represent the percent of cement in the binder, and the pie charts represent the composition of cement, fly ash, and slag within a typical concrete mix for these regions. And if we take two states that have different amounts of binder, but more specifically a different composition of the binder, we see that Nevada, the state with the typically higher amount of Portland cement per meter cube of concrete, leads to a higher 50-year uptake value. So information about the material definition definitely affects the magnitude of carbon uptake potential. Local data also includes information about the climate, which affects the exposure conditions, specifically for surfaces that are outdoors, because climate includes a breakdown of rainy to non-rainy days. Again, this map shows a gradation of the percent of rainy days in a given year, where the lighter blue colors are the drier states on average, and the darker blue are the rainier states. And going back to the same example, even if we assume the same amount of Portland cement for both of these locations, Nevada and Maine, Nevada is relatively drier in climate, and Maine is Maine is relatively rainier. One second. Yeah, so what we see is the climate affects both the rate of carbonation K, as the drier location has a higher rate of carbonation, and it also affects the degree of carbonation, the DC factor there, as the rainier state actually has the higher degree of carbonation. Accounting for both of these factors together, in this example, we see that in the drier location, there's a higher 50-year uptake potential per meter square of concrete surfaces exposed. So the breakdown of exposure, outdoor exposure conditions also affect carbon uptake. And Lastly, local data includes housing data or other information about the building stock, which helps us define the archetypes, which in turn helps us identify the breakdown of compressive strengths, because you have a variety of different building elements and building heights that could lead to higher or lower compressive strength use. The material definition, for instance, some archetypes have infill walls, which are concrete masonry units. Others have concrete structural frames, and these are, it affects the breakdown of mortar applications versus concrete, cast in situ concrete applications. And the archetypes also inform exposure conditions, because it helps us break down the amount of surface that's outside, outdoors, versus indoors, versus in-ground, such as the foundation. Archetypes also define the geometry factor, which converts the volume of cement to the surface area of concrete or mortar applications, as well as the service life, the square root of which directly scales the amount of, at least in the use phase, the amount of carbon uptake potential. So over the years, we have a number of existing homes, and each year we see new homes getting added with the new construction. And if we take a snapshot of any given year, there's various surveys that inform new construction, such as the Building Permit Survey from the US Census Bureau, and then a different set of data that informs the buildings that already exist, such as the American Housing Survey, again by the US Census Bureau. And there's similar data sources available for commercial or industrial building types as well, such as the Commercial Energy Consumption Survey from the Energy Information Agency. So the data sources that we refer to include the US Census Bureau, the Energy Information Agency, and actually the Federal Emergency Management Agency, because they have this detailed database of the national building stock. So any given locality with buildings gets represented as a combination of these archetypes, varying from low to mid-rise to high-rise structures, to residential to commercial to industrial building types. Now, if we look at an example of a single-family dwelling, looking at the kilogram of CO2 use phase uptake per meter square of living area or floor area, a large portion of that comes from the basement walls, because the basement walls are CMU units and have this high potential for carbon uptake. And then compared to a commercial structure, basement walls are de-emphasized, and the CO2 uptake potential mostly comes from the foundation slab or the structural frame, where in the single-family dwelling, the structural frame was not assumed to be cast in situ concrete. And what we see is both, so there's a differentiation between the archetypes in terms of carbon uptake potential per floor area. Did I do something? Okay. So the potential per floor area is higher for the single-family dwelling, but when you sum it up for the entire unit of archetype, both the use phase and the end-of-life uptake for the commercial three-story building is higher. But then we also need to account for the binder composition to calculate calcination emissions, and then we see that the percent sequestration is actually higher for the single-family dwelling at 35% compared to 15% sequestration in the low-rise commercial structure. So there's a lot of different factors that go into this calculation, and it's really important to identify the metric that we're interested in, because it could, like the archetype that gets emphasized could vary based on the metric that we're choosing. These are results from our national study considering buildings, pavements, and other infrastructure types. And this is our estimate of carbon uptake starting from year 1940 through 2020, accounting for cement production over these years. The stacked areas represent the different archetypes considered, and the black line that progresses over time is the uptake fraction, which is a fraction between the annual carbon uptake divided by the annual cement emissions. So the uptake represents the existing building stock in any given year, and the calcination emissions represent the cement production of that year. And those percentages are plotted on the second y-axis. The two things I want to emphasize is buildings are very significant. Similar portions of this uptake comes from buildings that are in use, infrastructure that is in use, and the end of life of both of these archetypes. But across these three broader categories, where the buildings, like the blue ones are the building archetypes, the yellow ones are the in-use pavements and infrastructure archetypes, and the green areas are the end of life of, that includes buildings, pavements, and other infrastructure. But the largest percentage comes from the in-use uptake of buildings. And the interesting thing about buildings, which other examples will reiterate on this idea, although a small fraction of the cement usage goes to the concrete masonry units in the exterior wall and the basement wall, a large portion, like a significantly disproportionately larger portion of the carbon uptake occurs in these elements. Overall, in the recent years, our estimate is that there's a potential for carbon uptake to neutralize around 15% of annual nationwide process emissions. And statewide, carbon uptake could neutralize 5 to 25% of annual statewide process emissions. And this is our estimate for the year 2018. So that plot shows the percent sequestration of calcination emissions by carbon uptake based on our estimate. And the lightest blue is the 5% value, and the darkest blue represents the 25% value. And there's a variation across the states, which relates to factors like the construction rate and other information as well. But one key piece of information that we found that had a high impact on these variations is the breakdown of mortar to concrete applications. So comparing the meter cube of elements that include mortar to the volume of elements that include cast in situ concrete, we see that there's higher potential for carbonation in states that have a larger portion of mortar applications compared to cast in situ concrete applications. And we found a similar trend comparing Mexico and the United States, where Mexico, the first plot is cement production over the years, and Mexico has about half the amount of cement production, but a very similar magnitude of annual carbon uptake, mostly because the cement is being used in higher proportions in these mortar applications, lower compressive strength applications like single-family and multifamily uses, which are represented in the blue bars, and building applications. So key takeaways. Carbon uptake is crucial to accurately assess both the benefits of cement-based products and to accurately assess the need for emissions abatement solutions. It's significant and has the potential to neutralize annual process emissions by around 15% nationally and 5 to 25% on a state scale, as shown in the US study. It's actionable because we see this variation between archetypes and elements and contexts. Thus, it could be increased by channeling the cement usage to these specific archetypes or elements or contexts. And it's not just governed by the amount of cement consumption, as shown in the Mexico study. And finally, carbon uptake is possible to model at high resolutions, as demonstrated by our bottom-up approach, capturing these local variations in archetypes, in material definitions, and exposure conditions, which affect the carbon uptake magnitude at various phases of the life cycle. And I'll take questions now, But if you guys want to reach out to me, my email address is my name, bensu@mit.edu, and we always have resources and tools available on our lab website as well, which is cshub.mit.edu. Thank you.